Okay. So, we are looking at forward chaining, and we want to look at an efficient way of doing this match process, and we will look at this algorithm called the Rete algorithm, which does this thing very efficiently. This was devised by a guy called Charles 4G, and he published his PhD thesis I think in 1979, and that was his PhD thesis essentially. Subsequently, of course, he went on to found a company which is doing rolling business, because forward chaining in rule based systems is something which is very popular in the industry, especially things like banking industry, which likes to have their managers write the rules and somebody else do the reasoning for them. And the whole idea of expert systems was basically that you separate the knowledge part with the reasoning part. You have an inference engine which does the reasoning for you, and the knowledge is provided by the domain expert essentially. So and it is quite popular in many areas essentially. Okay, so we have a knowledge base which we call as a working memory, and the data is the working memory elements. By data we mean the facts essentially. And then we have rules, which are, so this whole way of looking at things came from Newell and Simon, who did a lot of work in how humans solve problems. In fact, they wrote a book called Human Problem Solving, and remember that Simon was a economist by training essentially, and they looked at all kinds of things. So, their model of cognition, if you might say, was that we have a long term memory and a short term memory. The long term memory consists of rules of the kind that we know what are the associations between things and that kind of stuff. So, all men are mortal, for example, is part of our long term memory. Short term memory is concerned with the problems that you are trying to solve at hand essentially. So, it is a data concerned with the problem that you are trying to solve essentially. So, in some sense the working memory corresponds to short term memory. Anyway, we are not interested so much in the psychological aspects of this, but we must be aware of this fact. Whereas, the rules they correspond to long term memory, and the whole thing is that we employ or we exploit our long term memory to solve problems which are stated in the short term memory essentially. So, if you remember the inference engine algorithm that we had seen, what we have is a working memory or the set of facts, and this working memory is taken by this match algorithm along with a set of rules, and remember that the rules correspond to long term memory. It produces, we mentioned briefly in the last class, something called a conflict set. So, just remember that the conflict set is a collection of rule and matching data combos in some sense or pairs, each rule with its matching data in the conflict set. This was fed to a resolve component, which essentially picks a rule. So, we can denote it by some rule R I and along with the data, and that rule is given to the execute component. Remember, it is a 3-stage process. And this produces two kinds of tokens. One is plus working memory element, which means you are adding a new working memory element, and we will look at the language in a little bit more detail in a later class. Today, we are simply focusing on the match part essentially. Or they may produce another kind of token, which is a negative token, whose meaning is that you want to delete that working memory element from your working memory essentially. So, you either add new elements or you delete new memory elements, which basically mean that you are making changes into the working memory, and therefore, you have to go through this whole process again. So, towards the end of the last class, we had said that because we are allowed to delete things, you are forced to do this match all over again essentially. But what the Rete algorithm tries to do is to carry forward. So, this word Rete actually comes from Latin, and in Latin it means a network essentially, and we will see that essentially what this Rete algorithm does is to organize the rules into a network essentially, and that network is called the Rete network. So, it is a kind of redundancy because Rete itself means a network, but still. So, what the Rete network does is that it makes a change into this part of the process. It redoes this in a different way. What it does is that, so it is trying to, so the goal is to try to carry forward as much match as you have done in the previous. So, remember that once you go do the match process, that means you have looked at every rule, try to match it with every piece of data and made a list of what matches with what essentially. Now, after the execute step, some of that will get disrupted, because either new elements have been added to the data, which means new rules may match, or some elements have been deleted from your knowledge base, which means some of the rules which are matching in the previous cycle will no longer match in the next cycle. So, which is why we thought that we need to do the match all over again, but if you are doing brute force match, then you see that you have to match every pattern with every data, and it is a very expensive process. What the Rete network tries to do is to carry forward as much as we can of the match done in the previous cycle and only account for the changes essentially. So, we can see this part as follows, that we accept changes in working memory. The match algorithm, as we defined earlier, takes the working memory and tells you which rules are matching with that working memory. The Rete algorithm takes changes in the working memory and it feeds them into what we will call as a Rete net, which is essentially a compilation of rules. So, the Rete net is just a representation of a rules in a network format, and what this Rete net gives us is changes in the conflict set. So, remember CS stands for the conflict set. So, this is a change that we are making here, that we will only look at changes, because when we talk about changes, then these are the changes that are being made here essentially. Either a new working memory element is being added or the old working memory element is being deleted, and we essentially want to look at what is the effect of these changes onto the conflict set. So, it takes as input as changes to working memory and output is changes to conflict set essentially. So, let us start by looking at the Rete network today, and in the next class we will see an example which will make things a little bit clearer essentially. So, I like to think of the Rete network as, so it is a network which has a root just like a tree has a root, and that is the place where we enter changes in working memory, and then it is a kind of a network which is what we will study, and in some sense you can see things hanging from below. This is just a way of visualizing things which I use, and what is hanging from here is basically rules essentially, the set which is a conflict set. So, basically what you have is some rule with matching data, another rule with matching data, and so on essentially. And we can think of the network as made up of two parts. The top part is a discrimination network. Other terms. So, basically what this discrimination network does is that it is like a, if you like the analogy of networks, it is like a packet switching network. And the packet in question is a working memory element, and essentially the content of that working memory element is treated as, you might say, an address of the destination rule that working memory element is destined to match essentially. So, the discrimination network is basically it kind of separates things which have to go to different places essentially. That is why it is called a discrimination network. Similar names that we use are, for example, if you have studied decision trees, the same idea holds that you put something in the top and then it sort of gets distributed to various destinations. The basic idea is similar to what we do in binary search trees or any search trees for that matter. But in binary search trees you have a data element or a key or a token, and depending on whether its value is greater than some test that is being done at that node, it will either go left or it goes right essentially. In higher order search trees it may have many branches essentially, and in decision trees the test may not necessarily be numerical, it could be a test of some other kind essentially. So, for example, you may test for a string matching or any such thing, any kind of a test is allowed essentially. And the discrimination network is basically an idea which comes from a decision tree networks, is that you put a token on the top, and what is a token? In our case, the token is a working memory element. It may come with a plus sign or a minus sign. Plus sign will mean that it may go and trigger a rule, and minus sign may mean that it may go and cancel a rule which is already matching essentially. But essentially it has to find the rule that it matches essentially. That is the main task of the match essentially, and the top part basically separates the data according to the destination rules that they are meant for essentially. So, these are nodes, it is made up of nodes which are called alpha nodes. This is a terminology devised by Forgy. What they do is to test for a condition. So, an alpha node will get a token, it will do some test for a condition and it may send off the token into one or more of its different children essentially. So, the top part of the network can be seen as a tree essentially, where you start at the root and then gradually you keep branching till you reach the destination essentially. So, the destination is the rule that it is meant for essentially. So, what is an advantage that we are doing here? One advantage is that if a working memory element matches many rules, the testing is done only once. Because it is a network and you are sort of in some sense you are throwing the token down from the root into the network, it will follow some path and that path may lead to more than one rule essentially, because the rules are hanging at the bottom of the network essentially. So, that is a plus point. Of the Rete algorithm essentially. The other plus point comes from the fact that we are only looking at changes in working memory essentially, which means that whatever is hanging at the bottom of this network will continue to hang there. So, when I say hanging, I am just using my own sort of visualization method. So, it is the rules which have already received matching data. So, just imagine the process that we are starting this whole process when there is working memory is empty. So, we only have the network and obviously, there is no data. So, nothing matches. So, there are no rules in the conflict set, but as you keep putting in data, as you keep putting in the working memory elements one by one, they keep traveling down this network and eventually when enough data has collected for a rule to match, then a rule is created at that point essentially. So, these are rule nodes which are created when matching data is found essentially. So, the top part they in some sense find roots for working memory elements. If you just use a network analogy, they tell the working memory element where they have to go. The bottom part is assimilative. So, these are beta nodes and what they do is they collect working memory elements needed for the rule So, if a rule has let us say n antecedents, that means there is pattern 1, pattern 2, pattern 3 up to pattern n, or antecedent 1, antecedent 2 up to antecedent n. It needs n pieces of data before the rule will match essentially. Okay. And what the bottom part of this network is basically it collects data. So, one piece of data may come from here, another piece of data may come from a different place in the network, and the beta node essentially collects data. What does the beta node do? It checks that shared variables match the same constants. So, if there is a variable, so a rule may have more than one variable, and maybe towards the end of this class we will quickly see an example, and then we will work out a more detailed example in the next class. So, one thing it does is it checks that a shared variable. So, if a variable is coming from here, let us say x, and it is also coming from here x. So, it is part of some rule essentially. Okay. And so, a rule basically needs let us say two patterns which are coming from different directions. You want to make sure that the same data is matching that essentially. So, I will shortly give an example essentially. So, this may feed to another beta node along with another piece of data coming from here. So, one may come from here, one may come from here. So, it checks that shared variables match the same piece of data, and the join, if you want to use the term, is done based on the antecedents needed by a rule. Because you want to collect together all those tokens essentially. So, what the beta networks do is they take those two tokens which are coming from the two parents and put them together to make a combined token. So, if a rule has for example 4 antecedents, then there would be 3 beta nodes which will sort of take 4 tokens and put them together. So, here we have 2 beta nodes which are collecting 3 tokens, and if you add one more token you will have to add one more beta node somewhere essentially, right. And then once you have all those tokens which a rule needs, then it is simply added to the conflict set essentially. So, the top part of the network separates the tokens essentially according to where they should be going. The bottom part of the token assimilates the tokens that you need for a rule to match essentially. So, let me give you a small example of a rule. The notation may be slightly different from the one that we have used in FOL, but we will sort of gradually reconcile to that essentially. We will see that these rule based systems are essentially versions of what we are trying to do in logical reasoning essentially. So, I may have a rule which looks like this. So, let us say rule and let us say it has a name and it is called total marks. And it may have a certain. So, instead of saying if, I am saying rule essentially. So, what you must learn to navigate between these different notations. This rule name I am using here, but if you look at the book like Brackman and Levesque, which we are also following, they use if essentially, but it is the same thing essentially. So, there is a rule and we are allowed to give a rule name, which of course, logic we do not really talk about. but let us assume that we have, and then we have the antecedents. So, let us say this is a notation that I use. So, the data is or the working memory elements are described in terms of something like a structure that we use in C. So, you might say student. So, in some sense this is a class name, and then I will use a notation which is used in a language called OPS5. It was one of the early language that was devised for rule based systems, and something which I am familiar with. So, the first pattern has a title called student, and it has a, so in this notation we have a class name, followed by attribute name and followed by value, attribute name, value, and so on. This is how a working memory element is described. So, it has a structure. So, the class name is student here, the attribute name is let us say name, and I am using a variable here. So, let me use a notation of OPS5, which is to put it in angular brackets. So, again this is equivalent to saying a variable called n essentially. Okay. It is just a matter of notation essentially, separating the variables from constants essentially. We need something. So, in first order logic we said we will use a question mark. In a language like OPS5 we put angular brackets to separate the variables. Then if you say marks, and let us say we have records in this format, subject let us say physics, it is a constant. Notice that physics is a constant, n is a variable essentially. Student, and attribute I have used the name student here, and student is a class name. There is no conflict, they come as we say from separate namespaces, and there is no confusion here essentially. So, you must learn to recognize that there is no confusion here. It is just an attribute name as far as this particular class called marks is concerned. So, marks is saying in this subject this student has so many marks, it has got 3 attributes and 3 values. The student must be the same student. So, I use the same variable name. So, if I use student name n, then in my marks I am looking for his marks or her marks. So, that variable must match exactly, and this is one of the things that those beta nodes do, is that when they accept these 2 tokens, one is a token called student and the other is a token called marks, it will make a check that if they have a shared variable, then the shared variable must match the same data. So, if I am talking of a student called Satish, then the marks must also be of Satish, otherwise you will all start complaining about the grades that you are getting. And the third is marks. So, and that is a value let us say M1 or something, or MP if you want to say for physics, and then I may have other subjects. Let us say we have only 2 subjects. Again I am interested in the same student, so I must use the same variable name, and so notice that the second and the third pattern are similar in the sense they are the same class name, except that they match different data. One matches physics, one matches chemistry, but they must match the same student name, and whatever marks we get we will do something with them essentially. So, I may have something like this, and in the language of OPS5 I may say something like make total it is a class name with student same total marks, and here a language may allow me to do something like m 1 plus m 2, which is of course not quite logical reasoning, but maybe if you get time we will see that addition and subtraction can also be seen from a logical perspective. But most of the time of course, we do not use theorem proving to show that 3 plus 4 is 7, we simply use a shortcut which is to add the two numbers. So, this is an example of a rule that may be used in OPS 5 essentially. So, the rule has three patterns. One says that I am talking about student who we will call as n, and then for physics n should have some marks, let us call it m 1. For chemistry, that student should have some marks called m 2. Then I want to basically create a record which says that the total marks of the student n is m 1 plus n 2. So, it is a job of the beta nodes to collect these three working memory elements. So, somewhere just imagine that you have this Rete network which has other rules of other kinds. For example, for grading there might be rules and all kinds of things might be there. And there we produce these three pieces of data, that there is a student called Suresh, then Suresh got let us say 70 in physics. So, that is one data record. Then Suresh got 65 in chemistry, let us say. The moment we get these three pieces of data, they will flow down the network, and then this rule called total marks will fire. So, we will have, when we get this data, one element added to the conflict set which says that the rule total marks is ready to fire, and it has got these three pieces of data that it is matching. And like this, if there are 50 other students, there may be 50 other rules, and then they based on the problem solving strategy, we may pick one of them using resolve and so on and so forth. So, the basic idea of a Rete network is that it is a two stage network. The top part basically discriminates between tokens, it sends them out into different directions. The bottom part is assimilative, it pulls together all those tokens that are needed for a rule to match, and at any given point of time in the Rete network there is a set of conflict set existing, which is a set of rules which are matching with data essentially. So, in the next class maybe we will look at an example to make this idea more concrete essentially.